So welcome to lecture 30 of MCS 471, our introduction to lecture. We will continue our version to initial value problems. So it's the third lecture on solving ordinary differential equations. But the lecture itself will be self-contained. So we will look first defining the local and global errors, and we will define the Euler method and the modified Euler method again. So we will see that the modified Euler method belongs to a class Kutta methods. So the modified Euler method is a two-stage Runge. Is that we can derive higher. The modified Euler method, as we have seen last time, is already good enough to approximate the trajectory for the pendulum problem. So we will come back to the pendulum problem, but we can now, by the method, by the higher order Runge-Kutta methods, we can compute much more accurate approximations for the trajectory of the solution of the pendulum problem. So we will end with a less trivial application from celestial mechanics, the so-called three-body problem. All right, let us then recall what are local and global errors, and we will see that this definition immediately follows from the truncation error of the Taylor series. Okay, what are we solving again? We're solving a problem. So here is the function derived, and the second ingredient is our initial value. So we are starting at x0, and we have a value y. We consider if we have a higher order equation, we rewrite the higher order equation as a first order equation. So we did this last time. But for the purpose of this lecture, we get back to the pendulum and the other application. We will view everything as one right function. So we discretize our problem. So remember again, our x here, start here, we have x1 and then x2. Size the step h positive value. And you can see that Taylor series come in very naturally. And where we truncate the Taylor series, we say that the order method is actually the error from the we did with Euler, we truncated the second term. And the Euler method that then has a second order local error. Minus All right, so the global error is n times the local error. Why is that? Well, typically, that's something that we have seen in the first lecture on differentiations. The problem is a lot harder. We can actually not go very far out. So the standard interval is between 0 and 1. In most applications, the independent variable is time, and then we let time go from 0. So then there is an immediate relationship between the n and the h. So h is 1 over n. If you have an h that is 10 to the power minus 2, that means that you do 100 steps to reach 1. And therefore, the global less. Local error is the error of the first step, error in the last step. But what makes it very hard here for this problem is that we have no backward error. We are working with test equations. So when we solved equations in the beginning of the course, we could always plug our values into an equation. We cannot do this here. With all right, let us indicate how you get Euler's method. You just truncate your Taylor series after the second term. So we start counting from 0. Important. So the local error is h. Error is h. The modified Euler method is here written as a predictor corrector method, where you recognize again the Euler's method. So you have the overlined y here, where, let me point it out. So the overlined method, the overlined is the implicit equation. So the modified Euler method is the trapezoidal method, but it had a problem that you can't really apply this. So we then said, well, you know, you can do these bootstrapping. The Taylor series were still fine. So we do 2 function evaluations. We do more work, but we also gain 1 order. And we've seen so 1 million steps with Euler method, we only got 6 decimal places. Going from 0 to 1, 1 million is 10 to the power 6. This is the value of n. H is 10 to the power minus 6. So the fact that you only get with Euler's method 6 decimal places is not such a surprise, because that's the global error. It's linear in h. With the modified Euler method, we can get 12 decimal places, twice as much as with Euler method. Now you could also say, hey, you know what? You did twice as many functions. Ha. Good point. That's why we are going to look at a more. But first, let us derive again the modified Euler method. Why is that important? Well, for the modified Euler method, we can still derive a very simple system can solve by hand and still explain the general principle after behind the Runge-Kutta methods. Derive the modified Euler method. Here is the general framework for use 2 function evaluations. So you could see this also as another way of programming, turning formulas into programs. And what is important here is that the number of stages equals the number of function evaluations. It's an entire fact, depending on two parameters. So the alpha and the beta determine where we are going to create the function for the second time. And the A and the B determine the coefficients in the combination of the two function evaluations. This sounds very familiar when we derived numerical integration formulas. We had some parameters in our rule. Here now we also have rule, what we call it a method. And we are no longer computing areas. So the methods are similar to them. Again, the goal is to determine rules or methods that are as accurate as possible. How do we do this? We look at the Taylor series. So we did this already. So the stage Runge-Kutta method. Combine this in one rule. So of derivation. If turn here evaluation, it's a function evaluation. Hard to work with, but we can simplify. Taylor series applies in series. We touched on that also when we considered Newton's method, several variables. So it's not the first time that we encountered Taylor series into variables. You could view this as a linearization. We replace function by a linear function. So the first point is where we start, and then we have the delta x and the delta y multiplied with the partial derivatives with respect to x and with respect to y. So here you recognize the linearization of the function. And with this form now, we have a simplification. So also we stop with to the first here. Well, we are multiplying this with a factor that will depend on h. So we are already, so the f is already equal to the first derivative. So we are already in a second order. So we don't need to go further. So for our purposes here, a linearization will do. And what does this linearization buy us? So what the point that I'm trying to make is that when we go to the bottom line here, that the two equations are not the same. No, they're not, but they have the same order. So from the purpose of determining the parameters in the rule, the A, the B, the alpha, and the beta, it's fine. So this is a rewrite that is justified. All right, so let us now look at how we get the conditions. If we now start to compare the terms in the series. So what do we get? So we have the Xn+h that's developed with Taylor series. So the functions are the approximations. The y at Xn+h is actually the actual value. If you would expand the Taylor series to whatever order, then we will converge to the exact value. Again, assuming the uniqueness and suppose that this is a well. I shall with the assumption that the partial derivatives of the function f are well defined. All right. So what do? We have our Taylor series that we will truncate after the second term. So we want h to the power 3. That the h and the a plus b have to agree. But we still have to deal with this second term. So what we did, we applied the equation. So let me, so it's kind of subtle here, but this is actually the very shortest form of the equations. Y prime equals f. So we back form for the prime by f, and y double prime is the derivative. The derivative of f at the point xn, yn. Okay, let's do this now. So we take the derivative of x of function in 2 arguments. So normally, if y would not depend on x, it would. But the second argument also depends on x. So you have to take the partial derivative with the second argument, and then multiply this with the derivative of the second argument with respect to x. So this is the chain rule in several variables. All right, so then this gives us what the by an expression that involves the partial derivatives and the function f again. All right, this starts to clear up a little bit. So we have the last line, which is again a repetition of our two-stage Runge-Kutta, collapsed and simplified in one line. And we have our previous line, which represents the truncation of the Taylor series. And we can start identifying now the terms. So this will be done here. So you can recognize, as I indicated earlier, that a plus b, that alpha times b times h equals h squared divided by 2. And then we have the last term. Perhaps I should have started underlining. So here we have the last term, b times beta, that corresponds with this h squared divided by 2. So what the f and the partial derivatives are doesn't really matter, because they are canceling out when we identify the two expressions, yn plus 1, and from the Taylor expansion. So that's the second equation. The yn plus 1 the methods are actually here identical, because it's identical to third order error. All right, so we have 3 equations in 4 variables and 1 parameter. So real number. So we see indeed 5 letters, but one of them you can think of a small enough number h. We want to determine the alpha, determine our second function evaluation, and then the a and the b. All right, so time for some symbolic computation. We could do this probably also by hand, but it's actually good to look at the solution. So we have our variables, and then solve. So what comes out is that we have As you see that beta we solve for certain variables, a, b, and beta. So we have 4 variables, and beta equals beta. So that's what the last. So we have a 4 tuple. So there is a unique solution symbolically. Beta equals beta. So there is still a lot of choice. So A, we have a general formula for B and a general formula for alpha. So the way to read this is that alpha is beta divided by h, b is h squared over beta, and the a is the. But okay, so let's make a choice. So we will choose, and here this is with hindsight. We want to derive the model Euler method again. When we choose beta to be h, that's very nice because then alpha becomes 1. So not a complicated expression that solution. And then the a and the b are also h over 2. So perhaps pointing this out, there are whole families, and the reason why some families are more popular than others is that it makes a hand calculation much more comfortable. So the rules that we will see are historical rules meant for in the pre-computer time, when computers were still human. So that's worth remembering as well. All right, so summarizing up, here we have the modified Euler method that we can write in so practical. Writing the modified Euler method as a 2-stage Runge-Kutta method lends itself very well to execution, to a systematic program to run this. The point is also that the order is order 3. So the method that we have used to Euler's method, to derive Euler's method, also gives us a justification for the local error. All right, there is a whole family. One can derive midpoint rule. So remember from numerical integration, the midpoint had the same precision as the trapezoidal rule. There is also here a midpoint rule, a midpoint method that can be used just as well here in the Runge-Kutta methodology. One can get the point method by taking alpha 1/2. So the purpose of the exercise is to derive the midpoint method. If you think about it a little bit, so it's not intuitive algebraically, but the alpha equals 1/2. Remember that the alpha determines where we evaluate for our function. What is h? We are all right. With the midpoint rule, we take our second evaluation in the middle of the interval. Now, because if you have solved, so I only give you the value for alpha. If you solve this system now right, by construction, you will third order. So you will have the same accuracy as the modified Euler method. So verify that. So in essence, this is the reason why you have the third order, the local order. All right, let's just now apply our test equation again. The test equation has as exact solution the exponential. So we start at 0, x equals naught is 0, naught is. We run the modified Euler now as a two-stage Runge-Kutta method. Evaluation. K2 is the where you recognize the correction, the Euler term, Euler method. And then we have the trapezoidal rule. We define all our methods by Julia functions. So here it is. You see also the direct relationship between the h and the n. So in some of our functions, the leading parameter is n. When we think about the amount of work we have to, or we also can think about the accuracy, the h. Relationship between if you work on the interval 0, 1. So the method is defined now. It's very straightforward. And here you see the output on the test equation, where local error was expected to the power 3. So there is this. Sometimes the error is less, sometimes the error is larger. But you see the relationship between the local error and the global error. So there is this order difference. So here we read our numbers backwards. So we have the -4 from the local. So from the global error, we were expecting 10 to the power -2 because the h is 1/10. And the global error of the modified Euler is quadratic, cubic in local error. So but the local error is actually better. And why is this so? This depends on the partial derivatives of f. So one can intuitively see this, that close to 0, the exponential is still very flat. It starts to get very wild once you get past 1. All right, so far so good. Also, you have, if you solve the exercise 1, you have the midpoint rule. The midpoint rule belongs to the same family as the modified Euler method, so you have the same theoretical orders. Theoretical. The purpose of this second exercise here is that you verify the actual test equation of this. All right, now let's go to the more interesting Runge-Kutta methods. So in general, a p-stage Runge-Kutta method uses p function evaluation, and it has order p. And the p here is global. Sometimes we go up. So when we went from local to global, we did -1. If you go from global to local, you do +1. P in a p order Runge-Kutta stand for three things. The P from the name, so that's the zeroth thing actually, but it has the number of function evaluations and the order. All right, let us look at some examples. Here is a third order rule. So again, saying that this is the little words always have a lot of meaning here. So the little words, it's really a third order. So it's just one of the many. Here we have three function evaluations. And perhaps you may remember we did this again. Yeah, I will not dwell on this, but we have covered Simpson's rule. Simpson's rule now to me because we have, but the case actually not Xn+h. So because that would lead again to an implicit method. So we do not really have Simpson's rule here, but we have a 3-point method. That already gives us a good global error. So we may expect 6 decimal places if the h is 1/100. If the h is 0.01, then it will give us 6 decimal places. This corresponds to this. Is nice to look at, but we will not use this. We will not derive this. Only let's experiment with this. So it is a 3-stage. So 3 is the global order. So here we were actually expecting 10 to the power minus. So the global error is corresponds actually here quite well. So 3-stage. We were actually expecting 10 to the power minus 3 because the step size were actually not. Let me correct this. So the local error would be 4th order, and actually 1/10 we expect to the power minus 4, which is good. We see to the power 4 times 10. The global thing 10 to minus 2. We see 10 to the minus 4. Very good, actually. So this is what is coming up next is the 4th order Runge-Kutta method, where it seems here that we take 2 function evaluations at the same point, K2 and K3, but notice that the second argument is different. This is a famous rule with very nice numbers. So why is that? So there's a lot of symmetry here. This is very good if one has to do this all by hand. Now the global error is 10 to the power is h to the 4. So again, the 4th order, 4 stages, 4 function evaluations. You want 4 decimal places in your global error, then a large step size will actually do. And if you compute 4 decimal places is already quite tedious. So these rules are historical. So here we see that we get 6 decimal places now. 10 function evaluations. Remember Euler's method, for 6 decimal places we needed 1,000,000 steps. Here we do 10 steps. And again, with every step we do 4 function evaluations. So actually we do 40 functions in total. Good to remember work here that we do. So this is the first straightforward method evaluations. And here we have 40 function evaluations for 6 decimal places. All right, let us summarize this. So we ran Runge-Kutta method on the test equations, always doing not too much work, only 10 steps. The global error actually improved dramatically. We go from 20 function evaluations to 40. We do more work, but we gain quite a lot of accuracy. All right, let's do some variations. So we have the exponential function. What happens if we are adding a parameter there? So we are making the exponential function essentially tamer, flatter, if the lambda goes. Try to relate the error with the parameter. All our experiments with lambda equal 1. What if you start to take lambda 1/10 and lambda 1/100? Still fixing the step size, look at the local and the global errors. All right, 10 minutes left for our applications. So the pendulum problem is a second order equation. We have used this as our running example, or as one of our examples, to obtain a system of 2 first order equations. And now, because it's a second order problem, we need 2 initial conditions. So our first variable is the position, the second variable is the velocity. In general, numbers work out well if you have an nth order differential equation, n initial conditions into a set of n equations. We have now a system. So the purpose of these applications here is that they are illustrations to the application, so it's not an applied network, to show that everything is quite general. You can see our problem as now a vector problem. So our functions, the functions that we will derive, will return vectors. So the right-hand side, so the capital, so the big bold fat F is actually the right-hand side. So here it is, I'm circling it now. So here you see the most important thing. What is the big bold F? So that's the right-hand side. I'm using the second index in K2. The second index indicates the first or the second row. So purely formally, if we use bold letters for vectors, then our two-stage Runge-Kutta method is immediately generalized. Notice the first all right, let us specify this now. Here you see the vectored version where we define the case, the K1 and the K2. Notice if you implement this, it's quite important. So we are So the last line is the combination of the function values, and the line before that evaluates f twice. All right, so we have the modified Euler method. We have the two-stage Runge-Kutta, and you see that the first two experiments are the same. We run this with a very limited amount of work, so we only do 24 steps. And from 0 to 2 pi. And you see that we start at pi over 4 to ending again at pi over 4. The 3-stage are still far off. The 4-stage already has 1 decimal places accuracy. And actually more close to 2 steps. So at the end, the global error is actually plotted out, printed. A picture says more. So here, the 4-stage Runge-Kutta method does essentially very little work, but still already plots a plausible plot. So summation with really a minimum number of points, but it is still plausible. So this kind of illustrates the power of the 4-stage Runge-Kutta method. All right. In the last lecture, we derived, we were using periodicity. So we were having curves, plane curves, that had a periodic, and here this exercise is the cardioid again. What you did in the previous, or what an exercise was in the previous lecture, was to apply the modified Euler method again. Here the point is, if you want to be, so then the problem there too was, what is the largest step size that you can take, the least amount of work, and still obtain a reasonably good plot so that it still looks like the cardioid. Now compare 3 and 4, the 3 and 4th order Runge-Kutta methods. That's the purpose of this exercise. If you want to continue, here is exercise 5 with another curve, same question. All right, I have about 5 or 7 minutes left for my last illustration. This is a 3-body problem from celestial mechanics. 3 bodies, you can think of the Earth, Moon, and Sun in 3 bodies, or you could also think about your spaceship traveling between the Earth and Moon. We see things in the plane to make things a little bit more simplistic. So we have 3 bodies, and we want to study how they evolve in time. The 3 bodies are determining, so there are again the equations here follow from Newton's laws, so that involve the acceleration, and it's compensated by the distances. So for the first body, you see that we actually, in the denominator, there is a funny square root in this, but you see that the denominator contains the distance of the first body to the second body in the first term, and also from the first body to the third body. And it also depends, so that's the correction term, so it's also a negative force. The correction term from the here. Now, I'm not good at explaining the physics and the justification for these differential equations. The main point is that the fourth order Runge-Kutta is actually quite accurate enough to compute some interesting solutions to this. Also, and perhaps most important before that, what this example shows is how you can apply, how you can go from the equation, the differential equation, to the program, to the Julia functions. And so we have second order. We go to first order. We have three second order equations for x1, x2, x3, and then three more for the y1, y2, y3. So we have 6 second order, which we turn into 12 first order equations, introducing new variables for the velocities. So the velocity component in the x in the first coordinate and in the second coordinates. So there's a lot of symmetry here. So here I'm doing the rewrite for the first body for the first component. So this gives us 2 of the 12 first order equations. So I will stop with a picture. So this is an interesting orbit, an interesting configuration that was discovered in '93 that gives a nice figure 8. So I stopped the simulation just before when the trajectories are going to overlap in each other. So we have the blue trajectory that goes towards the origin. So this is to where the third trajectory started. So the third trajectory, the initial position, was at the origin. And we have then the red trajectory that passes through the origin. So all three bodies, this is for unit masses. So the Jupyter notebook and the Julia program have the specific values in them. But the point being here, this is executed by a fourth order.